Section 8.1 is titled the geometric mean, and that's going to be a new concept for us. If you remember about a week and a half ago, we had a problem in our homework that asked us to find the arithmetic mean. And the arithmetic mean, we said that was just the average of some numbers. So, for example, if we asked you to find the arithmetic mean or the average between the numbers 3, 5, and 12, we would take these three numbers, we would add them together, and then divide by however many numbers there are. So in this case, there were 3. And if we add those up and divide by 3, we'd get 20 over 3. Or that would reduce down to, looks like 6 2/3. So we would say the mean of those numbers is 6 2/3. The geometric mean is just a little bit different. The geometric mean, it involves a proportion and it involves only two numbers. So what we're going to do is we're going to ask what is the geometric mean between two certain numbers. Well, to do that, we need to pretty much define what the geometric mean means. So let's say we have two numbers, and I'm just going to call them A and B. So we have a number A, and we have a number B. To find the geometric mean of these two numbers, we set up a proportion. We put A in the numerator of one of the proportions, or of one of the ratios. Then we put B in the denominator of the other. So we end up with A and B in these two spots right here and right here. Now what goes in the other two spots? Well, that's the geometric mean, and it's some number. And for this case, I'm just going to call it x because that's going to be our unknown. Remember, A and B are numbers. X is going to be my unknown. So how do we solve when we get here? Well, it's proportion. We would cross multiply and solve. And that would be that the product of A times B, so A times B, equals the product of x times x. And x times x is x squared. So now if we're going to solve for x, we take the square root of both sides, and the square root of x squared is obviously just x, and the square root of AB becomes some numerical value. So there's a couple ways to think about the geometric mean. We can say that the geometric mean of two numbers is the proportion we can write, where x is in these two spots of the proportion, or we can just say the geometric mean is the square root of the product of the two numbers we're looking for. So let's look at it in an example. Let's say that we would be asked to find the geometric mean. So I'm just going to abbreviate for this. Find the geometric mean between, let's use 2 and 50. So that's going to be our problem. We're going to find the geometric mean between 2 and 50. Well, I'm going to set it up both ways. One way is just that we're going to write the proportion. So we put 2 and 50 in these two spots. We then put x and x in those two spots. And now we're going to cross multiply and solve. 2 times 50 is 100. X times x is x squared, so those two cross products are equal. Take the square root of both sides, and the square root of 100 is 10. Now if we want to shorten it up and not write the proportion, we can just go right to this fact above, that the geometric mean is equal to the square root of the product of the two numbers that I'm given. So x equals the square root of 50 times 2, or x equals 10. So what does that really mean? Another use of the word mean there. Well, the original problem said find the geometric mean between these two numbers, 2 and 50. So that means the number 10 makes this proportion true. That 2 over the geometric mean, which we found, 10, is equal to 10, again, over 50. So here are the two numbers we were given, and here is the geometric mean that we found. Well, is this true? Well, it sure is. 2 over 10 would reduce to 1/5. 10 over 50 would reduce to 1/5. So that number 10 makes that proportion true. So let's try one more example. We're going to go right next to it. So we're going to find the geometric mean between, and the two numbers I'm going to pick are going to be 4 and 12. I want to find the geometric mean between these two numbers. I'm going to go right to the shortcut. The geometric mean is equal to the square root of their product, 4 times 12. So x equals the square root of 48. And we can go into our calculator and we can get an answer of 6.93. 6.93 would be the geometric mean between 4 and 12. There are a couple of theorems that I'm just going to call geometric mean theorems, and they both involve right triangles, and they both involve dealing with the hypotenuse of a right triangle. Now, the rest of this chapter, chapter 8, is going to be a lot of information about right triangles. So what we're trying to do here is set up a way that we can find pieces of right triangles if maybe we don't know enough information to use a Pythagorean theorem. So we're kind of setting up some proportions that we can use to help us solve some right triangles. The first theorem, theorem 8.1, basically says this. If we drop an altitude from the right angle, so I've got that drawn in red, we have an altitude. Remember, an altitude goes from a vertex to the opposite side at 90 degrees. So in other words, it goes from a vertex to the opposite side at 90 degrees. So there's the height of this triangle. Now, what is the side that that altitude goes through called in the right triangle? Well, it is the hypotenuse. This side is the hypotenuse. And the theorem basically says this, that the height, that's going to be h, that the height is the geometric mean of the two segments the hypotenuse gets split into. I didn't say that very well, but basically that altitude goes through and it cuts the hypotenuse into two parts. This part has a length of x, this part has a length of y. And the relationship that x, y, and h have is geometric mean. In other words, we put x and y into our proportion, and then we're going to put h in the geometric mean spot. In other words, h is the geometric mean between the lengths of segments x and y. Or in other words, in our shortcut, the length of h is equal to the square root of the product of x and y. And we're going to use that in an example here in just a second. Now, theorem 8.2 uses a few more pieces to this right triangle. So let's first of all look at the whole right triangle. And in this case, let me get to my pointer. In this case, we have a side A, or a leg B, and a hypotenuse C. Now that is of the entire big right triangle. Okay, I'll say that again. Leg A, leg B, hypotenuse C. Now when we take the height here, our segment in red, when we take the height and drop it from the vertex, which is at the right angle, down to the hypotenuse, just as we did in the problem above. We drop this altitude. It cuts the hypotenuse into two parts. It cuts it into a little part and another little part. And Theorem 8.2 says there's a relationship between this little part, x, and the leg that's a part of this little triangle and the whole hypotenuse. Again, there's a relationship between A and X and C. There's also a relationship between B and Y and C. And what is that relationship? Well, it's going to use the geometric mean. And the theorem says this, that the length of A, so this length right here, okay, the length of A is the geometric mean between the length of the entire hypotenuse and the little part of the hypotenuse. So if we write that out, we're saying that the length of A is the geometric mean between the entire hypotenuse and the little segment x. So it's a geometric mean between the hypotenuse and the little part of the hypotenuse that's right next to the leg. So in other words, if we were to cross multiply and solve, or use our shortcut, we could say that the length of A is equal to the square root of the product of C and X. And that's just a theorem, and we're not proving a lot of the theorems that we do in here, we're just taking them as true. And it's another relationship that right triangles have, in addition to a squared plus b squared equals c squared, which we'll hit a lot more later. Well, let's see if we can come up with that other relationship, because remember, I said there was a relationship between A and X and C. Well, there's also a relationship between B and Y and C. So let's see if we can write that relationship. Remember we said the length of the leg, in this case it's B now, we've moved to the other leg of the triangle. It is the geometric mean between the entire hypotenuse and the little part of the hypotenuse. So the length of B now is the geometric mean between the entire hypotenuse and this part of it. Or, in other words, the length of B is the square root of the hypotenuse times the little part of the hypotenuse. Now that one's a little bit more confusing, but we're going to put it in an example and kind of see how it works. All right, so here's our first example that's going to use those two theorems. We're given that we have a right triangle, and we know the hypotenuse is divided into segments of 6 and 24 by one of the altitudes of the triangle. In this case, it's this altitude. It comes from the right angle to the hypotenuse. So there's several pieces of information that are given, and we can actually use this information to find z and find y and find x. So let's first of all use theorem 8.1. Now if we go back to 8.1, it said that the height of the triangle, so the segment in red, is equal to the square root of the product of the two pieces of the hypotenuse. So if we apply that to our problem, we're going to say that the length of y is equal to the square root of these two pieces, 6 times 24. So y is going to be equal to the square root of 144, and the square root of 144 is a nice even 12. So the length of y is now 12. Okay, we found one piece. Now we need to find x and we need to find z. Well, let's go up again and look at theorem 8.2. Theorem 8.2 says that the length of one of the legs is equal to the square root of the product of the entire hypotenuse times the little piece that's adjacent to it or next to. So let's use that fact as we try and move up here. It says that the length of a leg, so let's do z first, is equal to the square root of the product of the entire hypotenuse. Now in this case, I didn't give you the entire hypotenuse, but you can figure it. The length of the entire hypotenuse is 30 times the length of the piece of the hypotenuse that's adjacent to it. So we're finding z, so we're going to use 6. So it's 30 times 6. Or z equals the square root of 180. Now that one's not a nice even square root. So we're going to say that z is approximately 13.42. And I chose to go out 2 decimal places. Let's find y, or I'm sorry, we already found y. Let's find x the same way. X is equal to the square root of the product of the entire hypotenuse, we already found that to be 30, times the piece that's next to it, or adjacent to x. So if here's x, 24 is the piece that's adjacent to it, so it's going to be 30 times 24. Or x equals the square root of 30 times 24, 600, 720. If we take the square root of that, I'll get that square root sign off of there. Just do this. So x is approximately, if we go right to our calculator, 26.83. So we've used the geometric mean to find the height. We've used it to find one of the missing legs, and we use it to find the other missing leg. All right, on this next problem, it's kind of a crude drawing. It's kind of the best I can do. Now, this is an example from a problem out of your book where we have a person who's measuring the height of a waterfall. And the information that you're going to get in the problem is that the person's measuring the height of the waterfall and their eye level is 5 feet off the ground, so 5 feet. And also that they are standing 28 feet away from the waterfall. So the 28 feet would be the distance away from the waterfall, and that's going to be that segment right there. So what we're going to do is we're going to try and find what is the height of the waterfall. In other words, what we need to find then is this segment from eye level all the way up to the top of the waterfall. We're looking for this segment. And we can use one of our theorems to do that, except we're going to use it a little differently. What we've said is that this segment, which is the height of the triangle, is the geometric mean between the two pieces of the hypotenuse. Okay? So the height of the triangle, so in this case 28, is the geometric mean between the two pieces of the hypotenuse. Or in this problem, it is x, because x is this piece of the hypotenuse, and 5, because 5 is this piece of the hypotenuse. So if we cross multiply and solve, we're going to take 28 times 28, and that's going to equal x times 5, or 5x. And if we take 28 times 28 and divide it by 5, we get x to be 156.8 feet. So what we found is this distance, x, to be 156.8 feet. But the question is, how high is the waterfall? Well, we would normally think, well, 156.8 feet, but don't forget that you have this 5-foot segment right here. Because the person standing and measuring the waterfall, that eye level is 5 feet off the ground. So we would need to still add 5 to make up for the piece of the hypotenuse that we need to add in. So the height of the waterfall would be 161.8 feet. And so there's a case of how we might be able to use our geometric mean theorems in order to find the measure of what we might consider an immeasurable object. That you couldn't use a tape measure and measure the height of the waterfall, but by taking a couple of measurements and creating some right triangles, we could actually pretty closely find the height of the waterfall.